Welcome to part 1 of making a game engine. In this part we'll be drawing some graphics. But first, in order to do so, we need to understand today's graphics hardware. The hardware that we use today for graphics are known as graphics processing units. These are specialized processors designed specifically for drawing graphics. There's also a very wide range of GPUs with different architectures and features. However, in the 1980s, there weren't a wide range of GPUs available, so developers would write code for each piece of hardware that they would support. However, this started becoming an issue in 1994 when the Lion King game came out with drivers for many different types of computers. But some computers, such as compact computers, had many issues, and as such, Disney's support was flooded with parents complaining about the game not working. Microsoft, on the other hand, recognized this limitation of Windows, so Microsoft started working on DirectX. Gabe Newell started working on the porting project of Doom to be the first published DirectX game. Sega's Dreamcast would also support it, but DirectX would also later form the basis of Microsoft's game console, known as the Xbox. DirectX was known as an API, or an Application Programming Interface. Think of it like an interpreter. The program, or the game in this case, would speak to DirectX, and then DirectX would then speak to the GPUs that DirectX supports. As such, programmers would only need to really write code once, and it would work on the many GPUs that DirectX supports. There are many examples of these graphics APIs, such as WebGL, Vulkan, and DirectX. These APIs are generally designed for 3D graphics, but the same functionality can actually be used for 2D graphics. This game, for example, looks like it's in 2D, but you could rotate the camera and find out that there's a third dimension. Many developers don't actually use these lower level APIs, at least not directly. Many developers use a game engine, but of course since we're making a game engine, you might be wondering whether or not we need to use these lower level APIs. And the answer is that we actually don't, and this is because there are rendering libraries and rendering engines that can handle this for us. There are many examples of such as BGFX, threejs, and Filament. Some of the most popular games of today that use a custom game engine actually use these libraries, so you might have seen these in action already without realizing it. When using graphics APIs, they generally have a basic building block. Usually they are triangles. Take a look at this example. If you zoom into this image, you can start seeing some of the points where the triangles connect. But as you can see, it continues to remain clear and not pixelated or blurry. But it's important to note that each triangle has a cost. Having too many triangles on screens will require more time to draw everything on screen. But there are ways to add details without adding more triangles. With texture mapping, you could use images to create smaller details on the surfaces of triangles. Each point or vertex in a polygon mesh needs to be mapped like locations on a treasure map. On the other hand, you could use materials to change how light reacts to a triangle's surface. You could use textures or numbers as inputs for a material, such as albedo, metalness, specularity, etc. With all this knowledge, let's try to make something. As an example, I'm going to use this Minecraft compass, and we're going to spin the needle. With three.js, the first step is creating a scene. This is where we will place all our lights, cameras, and objects. You'll set the background color of the scene to gray. This will be useful later on. In case we get a black screen, we would know that the scene isn't working. However, right now you should get a black output, as a scene needs a camera. There are two types of cameras you could choose from: perspective and orthographic. Perspective projection allows objects to appear smaller when they're farther away. However, with orthographic projection, objects will always appear to be the same size, no matter how far away they are from the camera. Since we're making an animation, we're going to make a loop. And in this loop, we will tell the renderer to render the scene using the camera we've created. If you've done everything correctly so far, you should get a gray screen. The next step is to load in our mesh. Loading textures from a file could take an unknown amount of time, so you'll probably want to do this in the background. You also need to define the geometry and the material, the geometry being a plane and the material being the color of our texture. Afterwards, we add the mesh to the scene. Now you should get a really strange looking texture, and this is because the compass is repeated multiple times on the texture. We can fix this by using the repeat vector, which tells the renderer to repeat the texture on the texture map, but you can also use this to zoom in on the texture map. The texture doesn't need to repeat on the x-axis. so we will set that to 1. If you use 1 over 2, or a half, it will show half the texture. So for the y-axis, it should be 1 over how many frames we have in the texture, which gives us 1 over 32. The result should be a blurry compass. But if you played Minecraft, you would know that the compass is pixelated, not blurry. We can get the same effect by using a different magnification filter. The magnification handles pixels on the texture when they are bigger or the same size as a pixel on the screen. The default is usually linear, which uses an average of the 4 closest pixels on the texture. However, to get a pixelated effect, we want to just use the nearest pixel on the texture. You can also remove the black borders by changing some of the stuff about the material. You can make the material translucent, and this will give the object some special treatment where it will blend in with the objects behind it. Each texture's pixels have 4 values: red, green, blue, and alpha. The alpha value goes from 0 for transparent, 1 for opaque, and around 0.5 for translucent material. Some common translucent items where this is useful would be things like car windows or wax paper. However, this can be slow to render, and for this object, we don't really need to do any blending, so we can use an alpha test instead. Setting the alpha test higher than 0 will have the renderer not render a pixel if the alpha value is lower than the alpha test. Now, we can start animating this texture. This can be done by setting the offset in our loop. Right now it should be 0. And if we look at what frame is being drawn, you will see that we're drawing the last frame. And this is because 0 in our UV is the bottom left. So an offset of 1 minus 1 over 32 gives us the first frame. If we want to draw the second frame, we use an offset of 1 minus 1 over 32 multiplied by 2. I'm going to create a constant called the frame size, that will be 1 over 32, and the frame number, which in this example is 2. This gives us 1 minus frame size multiplied by frame number. And to animate the compass, we add 1 to the frame number every time we render in our loop. And if we want a looping animation, then we have to set the frame number to 1 when it gets higher than 32. After all of that, we should be finished, and you should have a compass with a spinning needle. And that concludes part 1 of making a game engine. If you have any questions, please write them in the comments. Thank you for watching, and have a good day or good night. I hope to see you next time.